So click means maximal complete subgraph. So we have to prove that clickation problem is NP hard. So in order to prove that problem is NP hard, so first we will be taking one theorem. Theorem is nothing but CNF satisfiability reduces clickation problem. So in order to prove the theorem, so first we will be taking formula. For that formula, we will be constructing graph and we will be checking whether the graph has click of size at least k or not, where k is the total number of clauses in the formula. So if the condition is satisfied, then the theorem is also satisfied. So if the theorem is satisfied, then we can say that click decision problem is NP hard. So and also click decision problem. So click is a decision problem, so it belongs to NP. So if the problem is NP hard and it belongs to NP, then we can say that the problem is NP complete. So now the second one is node cover decision problem. Second problem is node cover decision problem. So before proving this problem to be NP hard, so first we will check what is node cover. So a set S is a subset to the set of vertices is a node cover. A set S is a node cover for the given graph if and only if all the edges in E are incident to at least one vertex in the set S. So I am again repeating. So a set S is a node cover for the given graph if and only if all the edges in E are incident to at least one vertex in the set S. And cover size is the number of vertices in the set S. For example, if we consider this graph, for example, if we take the graph like this, so for this graph G, we need to find the node cover. Node cover. So in order to find the node cover, so first we will find the degree for each vertex. Degree for each vertex. Degree for each vertex. So here this graph is a directed graph or undirected graph. Type it in the chat box. This one is a directed graph or undirected graph. Undirected graph. Okay, good. So now tell me, what is the degree for 1, 2, 3, 4, 5? Type it in the chat box. So write down the degree for vertex 1, 2, 3, 4, 5. All the 5 vertices. So for 1 it is 2, good. Next. For 2 it is 3, good. So 3. Next. For 3 it is 2, good. For 4 it is 3, good. And for 5 it is 2, good. All of you check once now. So if you are following carefully, then the problem is easy. So here left side is the vertex, right side is the degree. So now we need to find the node cover for the graph. So without edges, first I will write the vertices. Now, so by using which vertices we can draw all the edges in the graph. So among 5 vertices, which vertices having highest degree? Which vertices having highest degree? Type it in the chat box. 2. Okay, good. 4. 2 and 4. Good. So first we will take 2. Listen carefully. First we will be taking 2. So if we consider 2, what are the edges we can draw? 1 to 2, 1 to 2, 2 to 3 and 2 to 5. See carefully. If we take 2, 2, so we can draw 3 edges. That is 2 to 1, 2 to 3, 2 to 5. Next highest degree is vertex 4. Vertex 4. Now, if we consider 4, so we can draw 4 to 1, next 4 to 3, next 4 to 5. 4 to 5. So if we take 4, we can draw 3 edges. Why? Because the degree is 3. So what are the 3 edges? 4 to 1, 4 to 3, 4 to 5. Now see, by considering only 2 vertices, 2 and 4. So have we drawn all the edges in the graph or not? Check once. Check once and type it. Yes or no. So this is one node cover. So node cover S equal to 2, 4. By using 2, 4 vertices, we can draw all the edges in the graph. By using only 2 and 4 vertices, we can draw all the edges. Next, for the same graph, another set is also possible. For the same graph, another set is also possible. So we will see that one. Now I am drawing only the vertices. Only the vertices. So in the first one, we have taken 2, 4. So what are the remaining vertices? 1, 3, 5. 1, 3, 5. So first I will take 1 and I will check. What are the edges can we draw? So for 1, what is the degree? 2. That means we can draw only 2 edges. 1 to 2, 1 to 4. 1 to 2 and 1 to 4. So here S equal to, so first I am considering 1. 1. Next, what is the next one? So I am considering 3. If we take 3, what is the degree? 2. So that means 3 to 2, 3 to 4 we can draw. So 3 to 2, 3 to 4. Next. So is it all the vertices completed? No. Still there are 2 edges left. So 5 to 2, 5 to 4. So we can consider 5. For 5, the degree is 2. So if you consider 5, 5 to 2, 5 to 4. 5 to 4. So 5. Here what is the cover size? 3. So here the set S contains 3 vertices. In the previous one, the set contains 2 vertices. 2 vertices. So like this, we'll be finding all the possibilities of the node cover. So first node cover contains only 2 vertices. By using 2, 4, we can draw all the edges. And the next possibility is 1, 3, 5. By using 1, 3, 5, so we can draw all the edges. So like that, we'll be finding all the possibilities for the given graph. So for this graph, only 2 possibilities are there. You can check for the third possibility also. You can try whether third possibility is also there or not. Have you understood them now? Then I will go to the problem. How to find node cover for the given graph. So first write down the degree for each vertex. Then take the vertices which is having highest degree and check whether they are covering all the edges in the graph. So here for this graph, the highest degree vertices are 2, 4. By using 2, 4, we can draw all the vertices. This is one possibility. So like this, how many possibilities should be mentioned for the given graph? It depends upon the question given. Suppose if it is small answer question means you can write only one possibility. If it is a long answer, you have to write all possibilities. So, okay, Satvik. So if it is a small answer, you can write any one possibility. If it is a long answer, you have to mention all the possibilities. So all nothing but you will not get more than 5. So if it is a big graph, then only you will be getting more number of possibilities. So if it is 5, 6, what if it means you will be getting less than 5 only. 5 only. Okay, now we will go to the problem. So first, so we have seen what is node cover. So in node cover decision problem, so we will be given a graph. We will be given a graph G and an integer K. We will be given a graph G and integer K. And we have to check whether the graph has node cover of size at most K or not. So we have to determine whether the graph G has node cover of size at most K or not. K or not. K or not. K is nothing but the click size. K is nothing but the click size. Click size. So in node cover decision problem, we'll be given a graph and integer K. And we have to check whether the graph G has node cover of size at most K or not. We'll see another example. Next, after seeing the example, next we'll be proving whether the node cover decision problem is NP hard or not. G here. So for this graph, find the click. Find the click. Click is nothing but maximal complete subgraph. Maximal complete subgraph. Complete subgraph. So find the click and write down the size of the click. Type it in the chat box for this graph G. First find the subgraph for this graph. It is complete. So 2, 3, 4, 5. So if you take 2, 3, 5, 4, 5, is it a complete? Complete means every pair of what is this must have an edge. Check once. Manikanta. No, 2, 3, 4, 5 is not a complete subgraph. Why? Because so 3 to 4 and 4 to 5 in the graph no edge. So 1, 2, 3. Good. Satvik. So 1, 2, 3 is a complete subgraph. 1, 2, 3 is a complete subgraph. So we have to consider the maximal complete subgraph. Here the maximal is with the 3 vertices. 3 vertices. If you take 2 also will be getting subgraph, but 3 is the maximal one. So here click size equal to 3. Click size equal to 3. 3. So K value is 3. K value is 3 and we have to check. Check whether we can find node cover size at most K or not. At most K or not. So 694 asking how 3 vertices map. So here see. So for this graph, so we have to find click. So the maximal complete subgraph is 1, 2, 3. So the click contains 3 vertices. That's why K value is 3. Click size is 3. That's why K equal to 3. K equal to 3. So now we'll write the degree for each vertex. Vertex degree. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. For 1, what is the degree? For 1, it is 3. For 2 also, it is 3. For 2 also, it is 3. Next, for 3, it is 2. For 4, it is 1. For 5 also, it is 1. It is 1. So, if we find the cover size for this graph, so what will be the cover size? So which vertex is having highest degree? 1, 2. So first we will take 1. So for 1 the degree is 3. That means 1, 2, 2 we can draw 1, 2, 3, 1, 2, 4. 1, 2, 4. Next, if we take 2, so we can draw 2, 2, 3 and 2, 2, 5. So we can cover all the vertices. So size S equal to 1, 2 and the node cover size is 2. So we need to check whether cover size is at most K or not. So 2 less than or equal to. At most means less than or equal to. So here K is nothing but click size 3. The condition is satisfied. The condition is satisfied. For G it is satisfied. Next. So we will construct the G dash for G. G dash is nothing but the complement graph for G. So G dash will contain edges that are not present in G. So first we will construct the complement graph for G and then we will check whether G dash has cover size at most n minus k or not. G dash has cover size at most n minus k or not. So here, what is G dash? So in G, so from 1, 1 to 2 edge is present, 1 to 3 is present, 1 to 4 is present. But 1 to 5 is not present. So we'll include 1 to 5. We'll not be including 1 to 2, 1 to 3 and 1 to 4. Why? Because G contains. Next, from 2, 2 to 1 present, 2 to 3 present, 2 to 5 present. Only 2 to 4 it is not present. We'll be including the 2 to 4. Next, from 3, 3 to 1 present, 3 to 2 present, 3 to 4 and 3 to 5 not present. We'll be including 3 to 5, 3 to 4 and 3 to 5. Next, from 4, only 4 to 1 is present. So we need to include 4 to 2, 4 to 3, 4 to 5. 4 to 2, 4 to 3 already included. So we'll be including the 4 to 5. 4 to 5. Next, for 5, only 2 to 5 to 2 is present. So we need to include 5 to 1, 5 to 3, 5 to 4. 5 to 1, 5 to 3, 5 to 4 already included. Already included. So now we'll write the degree. Degree. So I am constructing G dash and checking whether cover size has at most n minus k or not in the theorem. First we'll be taking formula and we'll be constructing graph and then we'll be constructing the complement graph for that graph and then we'll be checking whether the complement graph has node cover size at most n minus k or not. So that's why I'm constructing the complement graph. So for 1, degree is 1. Next, for 2, it is also 1. For 3, it is 2. For 4, it is 3. For 5, it is 2, not 2, 3. For 5, it is 3. So now we need to check what will be the cover size for G dash. G dash. So here the highest vertices are 4, 5. So I am considering 4. S equal to 4. 4. So from 4, we can draw 4 to 3, 4 to 2, and 4 to 5. 4 to 5. Next, if we take 5, so we can draw 5 to 3 and 5 to 1. 5 to 1. 5 to 1. Now, check. So whether all vertices, all edges, not vertices, all edges have been covered or not. So it has been covered. So here G dash cover size is 2, 4, 4 comma 5. Now we need to check 2 less than or equal to n means number of vertices in the graph. G has 5 vertices. 5 minus k is nothing but the click size for G. So G click size is 3. So 2 less than or equal to 2. Condition is satisfied. Condition is satisfied. So if the condition is satisfied, then the theorem also will be satisfied. If the theorem is satisfied, then also we can say that the problem is NP hard. So first we'll be taking graph, and for that graph we'll be constructing the G dash, and we'll be finding the node cover size, and we'll be checking whether node cover size is at most n minus k or not, where n is the number of vertices and k is the click size for G. So for G, the click size is 3. So 2 less than or equal to 2, the condition is satisfied. Now 694. So I asked some question. With the node cover vertices, we can design the graph according to the vertices. So if the graph is given, then only we can find the node cover. Without graph, how can we find the node cover? So with the help of the node cover, again we can draw the given graph. Next. So in order to prove the click decision problem, not click node cover decision problem, we have to take one theorem. The theorem is nothing but click decision problem reduces to node cover decision problem. So theorem Ncdp reduces Ncdp. So why we are taking click decision problem reduces node cover decision problem, not CNF satisfiability reduces node cover decision problem means. So whatever the graph we got in click decision problem, for that graph only we'll be constructing the complement graph. That's why here we have taken click decision problem reduces node cover decision problem. And also in the previous class we have proved that click decision problem is NP hard. That's why. So we are taking the theorem as CDP reduces NCDP. Now we have to prove this theorem. Proof. So let F equal to end Ci be the formula in CNF. Next, we construct graph G from F such that G has click size at least n minus k if and only if F is satisfiable. So this statement we have already discussed it in click decision problem. We will be taking the formula and we will be constructing the graph of that formula, and that graph will be having click size at least k. This one is k, not n minus k. K if and only if F is satisfiable. F is satisfiable is nothing but so whatever the formula we have taken, that should evaluate to true after assigning the truth values to some variables in the formula. Next. So we will construct G dash from G dash from G such that G dash has node cover size at most n minus k if and only if G has click of size at least k. So if the graph has kick-off size at least k, then G dash will be having node cover size at most n minus k. At most n minus k. N minus k. So G dash is defined as follows. G dash equal to V comma E dash. V comma E dash. E dash. So where E dash equal to U comma V such that UV doesn't belongs to E. UV doesn't belongs to E. So the complement graph will contain edges that are not present in the given graph. So first we have to take formula. For that formula we have to construct the graph and we have to check whether the graph has at least k or not. If it is satisfied, then we'll be constructing the complement graph and we'll be checking whether the complement graph has node cover size at most n minus k or not. If it is satisfied, if this one is satisfied, then we can say that the node cover problem is NP hard. So now we'll take one example. We'll construct graph and next we'll be constructing the complement graph and we'll be checking whether that complement graph has at most n minus k or not. F equal to x1 or x2 or x3 and x1 bar or x2 bar or x3 bar. So we have taken the same example in the previous class also. Here the formula contains two classes. First bracket one class, second bracket another class. So k equal to 2. And variables are three variables, x1, x2, x3. So in order to prove the entire formula to be true, C1 and C2 must be true. So in order to make either C1 or C1 and C2 to be true, so we have to assign truth values to some variables. I am assigning x1 equal to true. So therefore x1 bar will be false. I am taking x2 equal to false. X2 bar will be true. And also I am taking x3 equal to false. X3 bar will be true. So C1, if we take C1, so x1 value is true or x2 value is false or x3 value is also false. So it is true. C2 equal to x1 bar it is false, x2 bar it is true, x3 bar is also true. So it is true. So true and true equal to true. The formula is evaluated to true. So if now you can choose true also, 751 money teacher. So you can choose true to x3 also, not only false. So here the formula F is satisfiable. Why? Because it is evaluated to true. So if it is evaluated to true, if the formula is satisfiable, then the graph has click-off size at least k, where k is nothing but the number of classes. So here the formula contains two classes. Now I will be constructing the graph for this formula. F equal to x1 or x2 or x3 and x1 bar or x2 bar or x3. So here it contains two classes. So first class contains three literals. That's why left side I am putting three dots. The same example we have discussed in the previous class also. That's why I am going fast. So In C1, what is the first literal? X1. So the vertex will be denoted like this: X1 comma 1. X1 comma 1. Next, second one, X2 comma 1. Next, third one, X3 comma 1. So in the vertex, first one is the literal and second one is the class where the literal is present. So X1 is present in the first class. That's why X1 comma 1. So X2 is present in the second class, in the first class. That's why X2 comma 1. Next, X3 comma 1. Next, right side, second class. So what are the letters present? X1 bar, X2 bar, X3 bar. So first one, X1 bar comma 2. So X1 bar is present in the second class. That's why X1 bar comma 2. Next, X2 bar comma 2. Next, X3 bar comma 2. So last class we have discussed this one, G equal to V comma E, where V equal to sigma comma I, where sigma is a literal in CI. E equal to sigma comma I comma delta comma J, such that where I not equal to J and sigma not equal to delta bar. That means they should not belong to same class and same variable. So these conditions we have discussed in the previous class. So now we need to check. So here whether we can construct edges between these variables or not. So for our convenience, I am writing first one as 1, second one as 2, third one as 3, next fourth one as 4, 5, 6. So we cannot construct from 1 to 2, 1 to 3. Why? Because 1 to 2, 1 to 3 belongs to same class. And also we cannot construct between 1 to 4. Why? Because same variable. X1 bar belongs to same variable. So we can construct 1 to 5 and 1 to 6. 1 to 5, 1 to 6. Next, from 2 to 1, 2 to 3 we cannot construct. Why? Because same class. Next we can construct 2 to 4, 2 to 6. We cannot construct between 2 to 5. Why? Because same variable. Next, we cannot construct 3 to 1, 3 to 2. So we can construct 3 to 4, 3 to 5. Why? Because different variables, different classes. We can not construct between 3 to 6. Why? Because same variable. So similarly for 4, 5, 6 also. So we got the graph, and last class I have found this click size for this graph is click size for this graph is 2. So you can check with 5 vertices, 4 vertices, 3 vertices, 2 vertices. So if we take 5 vertices, it will not be complete. If we take 4 vertices, it will not be complete. If we take 3 vertices, it will not be complete. You will not get the closest one. So if we take only 2 vertices, so which is having edge in the graph J, that means 1, 6. It will be complete. Why? Because 1 and 6 is having edge. If we take 1, 5 also, it is complete. So since it is an undirected graph, 1 to 5 edge is there present means 5 to 1 also it is present. 5 to 1 also it is present. That's why. So here this one is complete. So click size is 2. Click size is 2. Now for G, we have to construct G dash. For G, we have to construct G dash. So here G contains 6 vertices. Left side 3 vertices, right side 3 vertices. G dash, we need to construct 1, 2, 3, 4, 5, 6. Now we'll check. So from 1 to 2, 1 to 3 and 1 to 4 edge is not present. So in G dash, we'll be including those edges. 1 to 2, 1 to 2, 1 to 3 and 1 to 4. So 1 to 5 and 1 to 6 G is having, so will not include. 1 to 5, 1 to 6 G is having, will not include. So from 1 it is completed. Next, for 2 to 1, 2 to 3 and 2 to 5 edge is not there. So we'll be including. 2 to 1 already included. 2 to 3 and 2 to 5. 2 to 5. Next, for 3. So 3 to 1, 3 to 2, 3 to 6 is not present. So 3 to 1, 3 to 2 already included. So we'll be including 3 to 6. Next, from 4, 4 to 5, 4 to 6. Next, 5. So this one will be the G dash. You can check. You can write side by side G and G dash. So you'll be getting G dash like this. G dash like this. So write down the degree for each vertex in G dash. So all of you type it in the chart box. What is the degree for each vertex in G dash? One, 2, 3, 4, 5, 6. So for 1 it is 3 good. For 2 also it is 3. For 3 it is also 3. You can check. So good. Manteja. So all the vertices having the degree 3. 4 also 3. 5 also 3. 6 also 3. All vertices having the same degree. All vertices having same degree. So now we need to construct. We need to find the cover size. Now, so every vertex is having the same degree. So you can start with any vertex. S equal to. I'm taking the first vertex, 1. So from 1 we can draw 1 to 2, 1 to 3 and 1 to 4. 1 to 4. 1 to 4. Next, for including the remaining edges. So we need to take another vertex. So I will take 3. So if we take 3, what are the edges we can cover? 2 to 3. 2 to 3. Next, 3 to 6. 3 to 6. So have all edges have been covered? No. Now, Maniteja, if you take 1, 2, 3, you cannot cover all the edges. Check once. If you take 1, 2, 3, you cannot cover all the vertices. Next. So in order to cover the remaining edges, I am considering 5. If we take 5, I can cover 5 to 4, 5 to 6 and 5 to 2. 5 to 2. See, have all the edges been covered? No. Still one more edge is left. That is 4 to 6. So you have to take either 4 or 6. Either 4 or 6. So you can take either 4 or 6. So I have taken 6 to 4. So here all the vertices having same degree. So you can get different combinations, but each set will be having the 4 vertices. minimum 4 vertices. Each set will be having minimum 4 vertices. That 4 vertices can be any 4. So here cover size is 4. Cover size equal to 4. 4. So we need to check whether cover size is at most k or not. We need to check whether at most n minus k or not. 4 less than or equal to. Less than or equal to. N is nothing but the number of vertices in the graph. So 6. N is nothing but the number of vertices in the graph. 6. 6 minus k is nothing but the click size. Click size for G. So this one is G dash. This one is G. For G, what is the click size? It is 2. So 6 minus 2. 4 less than or equal to 4. Condition is true or false? Condition is true or false? Condition is true. So condition is true means the theorem is satisfied. What is the theorem? CDP reduces Ncdp. This theorem is satisfied. Theorem is satisfied. So if the condition cover size less than or equal to n minus k. Cover size for G dash, what is the cover size? 4. Less than or equal to. N is nothing but the number of vertices, 6. So what is the click size for G? It is 2. So 4 less than or equal to 4. Condition is true. So condition true means the theorem is satisfied. So theorem is satisfied. What is the theorem? CDP reduces Ncdp. So this is equation 1. So we already know that CDP is NP hard. NP hard, that is, it is satisfying this condition. Satisfiability reduces CDP. This is equation 2. So apply transitivity. Applying transitivity to equation 2 and equation 1. Then we will get satisfiability reduces Ncdp. So this is equation 2, this is equation 1. So A to B, A to C. Then we will be getting A to C. So 248 Manohar asking in this whether we have to take click size for G or G dash. So click size you have to take for GM, not G dash. G dash. You have to take for G. So now, so if you after applying transitivity, we will be getting this condition. Satisfiability reduces node cover decision problem. So if this condition is proved means therefore Ncdp is NP hard. NP hard. And also, so node cover belongs to decision problem. So Ncdp belongs to NP. So if the problem belongs to NP and it is NP hard, then we can say that node cover decision problem is also NP complete. Node cover decision problem is also NP complete. NP complete. So if you understand easily, then this problem is not as tough as you are thinking. So just you will be taking the formula and you will be constructing the graph and you will be finding the click size for the graph. After finding the click size, so you will be finding the complement graph, and you will be checking whether that complement graph has node cover size at most n minus k or not. If it is satisfied, then automatically this problem is NP hard only. NP hard only. Now, have you understood? Type it in the chat box. Okay, ma'am. So still one more problem is there, and our graph problem. So we'll be discussing that problem in the afternoon class. Then, so graph problems will be completed. Subara sir.
Madam,
Okay, sir.
can I close the session?
After taking poll, you can leave, Amma.
Madam, there is no poll, madam, today. Hello?
Sir.
Madam, poll questions ichara, madam ki?
Madam, పంపించండి sir.
Okay, okay.
My students, after taking poll questions, you can leave.
Hello, Radha madam.
Subara sir.
Okay, madam.
పెట్టేస్తున్నాను.
Yeah. Radha madam, completed madam. Radha madam.